All right, the last example that we have for 2.8 intermediate value theorem is a really cool application, and it really shows you the strengths and just how really powerful the intermediate value theorem can be. So this example, we are to take any map and draw a circle on it. So let's just start by, let's just kind of, I'll vaguely freehand a map of what I think Montana looks like. Something like that, more or less. All right, so we've got Montana here. And let's just go ahead and draw a circle on it. Okay. So with that circle, what we're going to do is prove that at any point in time there exist two diametrically opposite points on this circle. So what does that mean? Well, that means two opposite points of a diameter. So two opposite points on a circle connected by a diameter. So we'll just draw a straight line from one end of the circle to the other. That kind of worked. It's a little bit in half. It's a little bit better. Okay. So with that there, let's go ahead and label these points. Label point A and label this point B. Okay. So now that we're on this circle, we want to prove that at any point in time, we can find 2 points that are opposites on the circle. So now I happen to draw the line from here to here, but everything else about this picture is fairly arbitrary. I'm not actually going to reference specifically what the angles are for these points. I'm not going to say that this is pi over 4 and this is, 5 pi over 4. No, I'm not going to say anything like that. So although the line is drawn like this, it might as well have been drawn like this. It doesn't really matter. This is arbitrary enough, but for the sake of drawing a diagram, I have to draw in a certain static manner. So this is that static manner, but you really should think of these 2 points as being anywhere on the circle, just as long as they are opposite ends. Okay, so no matter what time, we can always find 2 such points on this circle where the temperature is exactly equal. Okay. This also works on a sphere, so you can prove that on the surface of the Earth, or on a planet, there are always going to be 2 points, opposite ends, where the temperature is the same, which is pretty neat. Okay, so to get started here, what we are going to go ahead and do is we are going to sort of create our own intrinsic coordinate system to this circle. So I'm going to go ahead and I'm going to essentially say that relative to this line, this horizontal, we are going to measure counterclockwise a number theta, and this number theta is going to represent the angular coordinate on the circle. Okay? So, again, I'm not saying that theta is pi over 4, I'm just saying that to get to this point B, it's theta radians, whatever that means. So then that means over here at the point A, this would actually be represented by, well, it would be theta plus pi, since we have to go to the other side of the circle halfway around. So now let us define a function. So let f be the temperature on the circle with angular coordinate theta. So in other words, f of theta, that's what I should have here, this should be f of theta, reports back the temperature corresponding to the location on the circle with that angular coordinate. So for instance, f of pi over 2 would report back the temperature at the very top here. All right. So now that we have that, what we essentially want to prove, so we want to prove that we can find some pair of locations where the temperature at the one location, f of theta, is equal to the temperature at theta plus pi on the other side of the circle. That's what we want to find. Okay? Well, now this problem is set up just like any other problem that we've done. We have an equation. We now want to go ahead and subtract all the terms to one side and then define a new function. So we will let g of theta equal f of theta minus f of theta plus pi. So that's the difference. So now we want to check to see where this function g obtains a 0. So the important thing that's going to allow us to do this is the fact that many physical things, like pressure or temperature, they can change, but they must vary continuously. If one part of your house is hotter, maybe a south-facing window where the sun is shining bright in the Montana summer, and then you have maybe, not many Montanans have a basement, but maybe you've got, some part that's partially underground, that portion will be much colder. So if you start from the cold area of your home and walk towards that south-facing window, you experience every single temperature between the temperature of that cold space and the warm temperature of that hotter space. So whatever that temperature difference is, maybe it's the difference between 62 degrees and 75 degrees. As you walk from one location to the other, you experience 63, 64 degrees. Even, you can break it down even further, 65.2. 65 plus pi degrees you even experience, because temperature varies continuously. So we will mention that again in writing, but for now, let's just mention it in words. Okay, so let's go ahead and do this. So what we want to do here is actually think of an interval. We need an interval here. So let's add on to this and say that let g of theta equals blah, blah, blah be defined on a particular interval. Well, we want to start at our point in question. So let's say we start at the point B, for instance, whatever. And then if we're just trying to get to the other side, how far does theta have to go? Well, theta would have to go to plus pi. So the biggest theta really ever needs to be is plus pi, positive pi. Okay? So there we go. So now that we have that closed interval, let's go ahead and check to see what g of 0 is and what g of pi is. So g of 0 is going to be f of 0 minus f of pi, yes. And let's go ahead and see that g of pi is equal to f of pi minus f of 2 pi. But here's the neat thing. Remember that since theta is an angular coordinate, there is sort of a we're overcounting, right? We only really need 0 to 2 pi, really 0 to 2 pi with an open, a half open interval, because we don't need 2 pi because we have 0. Because on a circle, once you go one full rotation, you can call that starting location 0, you can call it 2 pi, you can call it any integer multiple of 2 pi. We can even call it 62 pi, and that would still represent the same location on the space. So really, because of this repetition and this periodicity, we can just rewrite this and say that f of 2 pi is the same thing as f of 0. Right? So just a little side note here, 0 is congruent to 2 pi mod 2 pi. That's a fancy way of saying it's the same. It represents the same location in our case. We're not saying 0 and 2 pi are numerically equal. We're just saying that 0 and 2 pi represent the same location. It's sort of like if you're talking about just times of the day, you only care about the time of the day. You know, if we're at 2 p.m., 26 hours ahead is the same thing as 2 hours ahead, right? 24 hours would take you to 2 p.m. the next day, and 2 more hours would take you to 4 p.m. Same thing with, years on a calendar, or not years on a calendar, months on a calendar. You can think about, 13 months ahead of time is really just 1 month ahead of time. Sure, it's a different year, but if you're only trying to figure out what the month is, you can just subtract chunks of 12 off. So in this case, this right here is telling us that we can just subtract off chunks of 2 pi, and then we get the same thing. It's called modular arithmetic. It's used a lot in computer science. Okay, so what we find here is that these two expressions look eerily similar. In fact, what we can do to this g of pi is I can factor out a negative, and then remember that when if you are starting with a difference of two things, factoring out a negative has the effect of switching the order of the difference. So what we can see here now is that this expression in front of the negative sign is the same as our expression over here of g of 0. So what this actually shows us here, this implies that g of 0 is just equal to negative g of pi, which is a way of saying that I'll just say, in other words, g of 0 and g of pi have opposite signs. And then what we've learned in the previous examples and videos is that if we know that the endpoints of an interval, if the value of the function have opposite signs, then you know somewhere between those two endpoints there must be a location where the function is 0. So I'll say, since temperature varies continuously, and g of 0 and g of pi are of opposite signs, by the intermediate value theorem, there is some angle theta between 0 and pi where this, let's say where g has a 0, i.e. there does exist a pair of diametrically opposed locations where the temperature is equal. Which I have always thought is pretty wild. And you can use this argument to show lots of things that vary continuously. There has to be some sort of equality, some sort of symmetry. The neat thing when you think about this is if you sort of think of taking this is a really big calculus idea that you'll explore in throughout Calc 1, Calc 2, Calc 3, depending on how far you go. So we proved this for some circle, and now we never once talked about the size of the circle. That wasn't important to us. But imagine that we were kind of keeping track of how big this circle is. I mean, we drew it in Montana, so it's obviously huge. But think about this art, because our argument didn't actually use how big this circle was. This applies for a circle of any size. And if you think about temperature change and how it varies continuously, if you think of this circle's radius as shrinking, so imagine what happens if we just shrink this down. Well, what happens to these 2 points on the circle as we shrink the circle down? Well, they obviously get closer to one another. And if you think about this in the limit as the radius goes to 0, you can think of these 2 points as merging and becoming the same point. And that should make sense on a physical level, because if we have temperature, it's going to spread out in this nice smooth way. So if we're approaching it from different areas, there should be some sort of way to merge back to that central temperature.